If we define a transformation as matrix multiplication, there is a property of matrix vector products that were really useful, this linearity property. If you define a transformation in terms of that, we will call it a linear transformation. So a transformation is linear if you apply it to a multiple and you can take out the multiple, and if you apply it to a sum, if you can split that across the sum. This is very much like a derivative. Now, why do we care? This kind of thing allows us to find the matrix transformation if we ever need it. If we talk about a transformation going from one space to another space, if I talked about transforming x, my x has to be in Rn, x1 all the way down to xn. You could write it in standard basis form. That means you could write this vector in terms of the standard basis vectors, I, j, k if you're in physics, right? If I'm going to take a linear transformation, I'm going to apply it to the left side here, and that means I get to apply it to the right side. Since all of those x's are just constants, and this is a sum of vectors, I can split this up because it's a linear transformation. The transformation of a sum ends up being the sum of transformations. And because there are constants inside, I can essentially take them all out. So I'll get x1 times the transformation on e1, all the way down to xn, the transformation on en. Now, by definition of a matrix times a vector, this ends up being a matrix where its columns are just the transformation applied to the standard basis vectors. So this thing ends up being A, this ends up being X. So this is what's given in your textbook in two different places, proposition 2.5.4, 2.6.2. If you are never told the transformation matrix, you can always find it by seeing what it does to the standard basis vectors. It will always be the case that the matrix of your transformation is just what it does acting on these individual basis vectors alone. In problems that we solve, we won't always be given the matrix transformation. We are going to have to find it. For example, in the discrete dynamical system problem, I could have given you something to do with just one of the car rental locations. If all of the cars start at location P and none start at location Q, that's kind of like a standard basis vector. How does the transformation affect it the next day? So for example, let's say I know the future state of this system. This matrix A is going to be the same as me taking those individual transformations, putting them in the columns. I'll end up having 1, 3, 4, -7, -5, and 4. The dimensions of this matrix are 2 by 3. I have to start with a 3-dimensional vector and turn it into a 2-dimensional vector. If I told you that I would like you to use this transformation to see what the image of 1, 1, 1 is, then essentially I would have to take this standard matrix and multiply it onto the vector 1, 1, 1. It's going to be one bunch of this vector, one bunch of this vector, and one bunch of this vector. This will end up giving you 0. So the image of this vector 1, 1, 1 ended up being 0. Now, it's often going to be the case that we are interested in which vectors take us to 0. So this is kind of a special problem. Which inputs x give t of x equals 0? The set of all of these inputs is called the kernel of t. We'll denote this as KER of t, kernel of t. We won't deal with that too much right now. It's just something that I want to plant in your mind. A little bit later in the course, we'll get to studying problems like this a lot more. So there are two final things that will come up. One is what's called the composition of transformations. Can I apply one transformation to another? When we talked about the dynamical systems, we said the state of the system on day 1 is taking the transition function and applying it to the initial state. Take this transformation and apply it there. If I wanted the state on day 2, I would have to apply this transformation to the state on day 1. And that's kind of like saying apply the transformation to the transformation on day 1. This is what's called a composition of transformations. So in terms of a function, you could call this t circle t on x0. This is going to be defined as a composition of functions. This basically says put two matrices together, one after another, and see what you get. this will give you a squared x of 0. T composed with t acting on x0 ended up giving you a squared x0. The point of the story here is that a composition of these linear or matrix transformations is still a linear or a matrix transformation. In general, if I tell you that I have t of x being implemented by this matrix product, and I have some other transformation s of x given like this, I'm just going to pretend all the dimensions work out. I could say s of t of x, take this answer a of x, put it into that function, and then that'll basically be a matrix times another one acting on your function. S composed with t acting on x has its own matrix, and it's just a product of the two. Another big idea that we're going to talk about, inverting them. Can I undo a transformation? So if I start with some vector here and I turn it into some other vector, there's its image. Is it possible for me to go back? Can I undo it? We're going to use this notation t with the minus 1. We'll say t with the minus 1 is the inverse transformation. If there is an inverse, so if this t inverse exists, we need this kind of thing to happen. If I apply the inverse to the answer that I got before, I should get back to what I started with. T of x is just a matrix multiplication. Now, if this really is a linear transformation or a matrix transformation, it should have its own matrix that I should apply to this to get back what I started with. So I think it's pretty easy to see what should go in this mystery box. You need that matrix right there to be the inverse. So the point of the story here is that T inverse will exist only if this transformation has an invertible matrix. And that means that A has to be n by n, and that tells you that this transformation can only go from a space to itself. You can't leave your space. You have to stay in the same vector space you're in. And if that's the case, then your inverse transformation will simply be the inverse matrix times what you've got there. So as a final little example, if I am told that my transformation is given by a of x, 6, -8, -5, and 7, is this transformation invertible? A good start is that this transformation starts in R2 and stays in R2. Does the inverse matrix exist? Yes. Your inverse matrix exists, therefore this transformation is invertible, and it has an undoing transformation. The undoing transformation is just the inverse matrix times whatever you started with.